Okay, welcome everyone again to this QRST seminar. For those that is the first time that you attend these seminars, this is the format. We will have two talks from Juan Miguel Arrazola, the first one, and the second one from Eliška Greplova. And the format is 25 minutes approximately, plus 5 minutes question. And you can ask the question in the chat and we will read the question to the speaker. And in case we are running out of time, we'll stay a little bit longer at the end of each of the talks, so we can discuss further any questions or comments about what the speakers present. Unfortunately, this time Juan Miguel has to leave early, so we will probably extend a little bit more his first talk, so he will have a little bit more time to answer the questions. So that's it. We are recording everything, and everything will be uploaded in the YouTube channel QRST, and with the slides of the speakers and the Zoom chat history. So without further ado, okay, Michał?
One more thing. Actually, I just wanted to let people know that we are organizing some meetup on Friday afternoon in Toronto, outdoor. So I will post in the chat more details. If anyone is in the Toronto area this Friday and would like to meet with other people doing quantum stuff, you are invited. And now, without further ado, passing it to Juan.
Yeah, that would be great. Finally, we can meet in person. So, okay. So let me introduce the first speaker, Juan Miguel Arrazola from Xanadu Quantum Computing. And he has a master in physics from the University of Toronto and a PhD in quantum information and physics from University of Waterloo. He worked as a research fellow at the Center of Quantum Technologies in Singapore before joining Xanadu in 2017, where he leads the quantum algorithms team. And Juan Miguel will present about software-driven research, which I'm really looking forward to hear this talk. So welcome, Juan Miguel, and thanks for accepting the invitation.
Thank you, Alba, for the nice introduction. Thank you for the invitation to the organizers and to everyone for attending. Indeed, I'm excited particularly about this talk. I often like to experiment and to force myself to go outside of my comfort zone. And this talk is one example of that. It's in a way an unconventional talk. So you are part of the experiment. Looking forward to your feedback and hopefully those will be useful. I want to start the motivation for what this talk will be about by sharing a perspective on research and software, but specifically a question that I get asked often, especially when I talk to younger scientists, but actually to scientists across the board, which is becoming more and more of a topic of discussion, right? Especially for young scientists in their careers in quantum computing. And it's what is it like to work in industry, right? We all get trained in universities, and a lot of us do a PhD in a university, and that's our first experience with research. So that's some familiarity with how this works, but what is it like in industry, right? And so I want to share some insights that I will hope will motivate the content of this talk, which is, well, I don't know the difference between academia and industry. It's a tough question, but some things that we can clarify. First, for some scientists, the idea of moving from an academic environment to an industry environment might actually entail a change of the subject matter of your work. So what I'm trying to explain here in this image is a situation where perhaps you're working on something like high energy physics, right? You're calculating cross sections, trying to detect physics beyond the standard model. And that's your subject matter, that's your expertise. But there isn't really an industry around these type of problems. So the move to industry might look something very different. Well, maybe you're transferring some of the skills, but really working on a different subject matter. And this is not the case for quantum computing. The reality is that if you're working as a researcher in quantum computing, you will still be working on quantum computing, right? What I'm trying to explain here is perhaps you're an experimentalist and you're an expert in cryogenic systems and dilution fridges. And what the change for you between academia and industry in terms of the subject matter may be simply that you're working on a different fridge, right? Now, obviously, there will be differences as well in the environments and how the research is performed. But this actually varies anyway between countries, between universities, between different companies. And I don't really know how things work in different places. So I don't want to talk about that too much. So my reflection is, so if we're working on the same subject matter, roughly speaking, quantum computing, well, what actually changes if we go in one deeper level of detail? What are the main differences in the type of research for quantum computing that may happen in academia versus the one that happens in industry? And my answer to that question is that the main difference is the role of software, right? My personal stance is that most scientists need to be good at their science, but also good at communicating, good at mathematics, and good at software. It's part of being a scientist to have some degree of skills, and that may vary between what you're doing exactly, but software plays a role. But in my experience, the main difference between an industry environment and an academic environment is the role of software in the research. And this is an image from the PennyLane website. And of course, a lot of this talk will be around PennyLane, that is showing that for the work that's being done in industry on quantum computing, especially on the theory side, one consequence of that work is the appearance of different software platforms, right? Of course, this is not meant to be comprehensive. I don't have, for example, Orchestra from Zapata. There's no Ticket from Cambridge Quantum Computing, and a lot of different software libraries. But this is something that industry does. So industry is more interested in creating products. And from the theory side, often that looks like creating software tools, right? And driving customers and people towards all the technology that are being built through the software. So software plays a bigger role. And this talk is about understanding the role that software plays in research, but perhaps from a different perspective, because the perspective that we're used to is that, well, software is usually used as a tool to drive research, right? Certainly this was my experience as a PhD student, right? We have a specific project. There's a problem that we want to solve, maybe a system that we want to simulate, some numerics that we want to do to confirm an idea. And so you write the software for the purpose of the research, right? And what does that typically look like? Not always the case, but typically it's one or two people, mostly one person writing the code. It's tested manually, if at all, right? And it's documented, if at all, just via comments, right? So it's really code that's built specifically for one purpose, which is typically having a research paper coming out of it. And that's what software that's driven by research may look like. Now, in industry, in my experience, it's different because you want to create software products, right? Now, there is also a role of research in the software. This is one that is very important to our team in PennyLane, which is that you want to actually implement existing research ideas, actually the state of the art. If you want to build great software tools, especially in a field like quantum computing, that's still growing, where still new ideas are being put forward, still new problems being solved, you want the software to reflect that, right? So definitely the software can be driven by research in the sense that through the work that we do on the research front, you want to incorporate that into the software. But the software itself will look different. First, it's not coded for a single person. It's coded for everyone to use. You want people perhaps that have no even experience with your code to go and learn and to employ it. Testing is really important. You don't want people to just get the wrong numbers and have like difficulties. So you have to test it, and typically this is done automatically, and you have to figure out how to do this. And documentation is also very important. Overall, the quality of the code, the quality of the software is much more crucial. You're actually creating a product, right? And how good that product is going to mean a lot to the success of your organization. And I think this is very important because ultimately what software is doing is turning abstractions into reality. That's how I think of video games, how I think of computer simulations in movies. That's one of the powers of software, is the idea to turn things that can be abstract, like music, like images, mathematical formulas, algorithms, and turn them into a reality, right? But we want to do it at the very highest quality. Now, this is the part that's maybe not too surprising about everything that I have said. But this talk is about a different perspective, which is the research that originates from the desire to build better software. And this is what I like to call software-driven research. And this is the main idea. When you're aiming to build great software, but specifically in our case in quantum computing, great quantum software, ultimately to reach a very high bar of quality, we need to solve research level questions, right? And what happens is that, again, in my experience, asking these software-related questions is a fertile ground for innovation. Right? One of the key challenges for scientists is to ask the right questions, right? To solve the right problems. And that's not always difficult to navigate. So what I'm trying to propose here and to share with you as an idea is that through understanding how we can build better software tools, we can actually derive great fundamental research results, right? And this is one of the main pillars of the philosophy and strategy of how Xanadu software and algorithms team works. So it's not just incorporating research, but we also drive research ourselves, largely based on the desire to build better software. So what I want to do in this talk is to give you examples of this point by telling you two stories. So it's a storytelling talk in the end, where I want to tell you about two papers that we have put out this year, which by the looks of it might look like just another research paper, right? Just hopefully a good one that you think it's important. But I want to tell you the story behind these papers and how they originated specifically from this desire to make penny lane specifically. And this is a big focus for my team, the best quantum software library for quantum chemistry, which is of course a big challenge. So I'll be talking about two papers, which you can see the links here. And I won't really tell you about the results. I won't tell you about how we prove things. I won't tell you about how the algorithms work. I'll give you a summary of the results, but mostly I'll try to motivate how we ended up with the results themselves. So let's get started. First, this paper on universal circuits for quantum chemistry. Now, so let's ask a question. We're trying to make great software that has different components. One question that's related to that is what makes software easy to use, right? User friendliness, that's always an important thing. And perhaps in your own experience, you felt that when there's a lower barrier of entry, or even when once you start using a specific tool, it's easy and you can do a lot of great things. That's a powerful thing. It's something you want software to have. But what does that look like? And this is not meant to categorize all forms of writing software, but to give you an idea of like different philosophies that can underlie how software is designed. One of them is like, well, easy means that you can do everything in a single line, right? You don't even have to think. It's just like ready for you. Everything's packaged, right? So this is kind of like a black box approach, as I would refer to it. And some code, here I'm using some Python type syntax. Could be something you implement this great software library, black box. You want to run some algorithm to solve some problem for some inputs. And all you have to do is write down this one liner. My solution is equal to the algorithm on my inputs. Boom, I'm done. And this seems powerful. This seems great. It seems very easy. But the reality is different. This type of implementation is what's referred to often as monolithic. It's like you build this thing and it just stays there. And that's all it can do. So it's extremely inflexible by construction. If you wanted to change different parts of this algorithm, right? If you wanted to maybe have a new idea that came out and change how things are, then it doesn't allow you to have that flexibility, right? And oftentimes trying to package things into something that is too simple is problematic because things are actually complicated. So you end up with like a lot of arguments and something that is actually very complicated, very heavy, ugly, right? So there's a lot of drawbacks from this type of approach. And the other extreme is something where it's a playground, where you simply don't package anything for the user. You just give them a lot of great functions, right? Almost like a sandbox. Here's a bunch of toys and build things, go crazy, like a Lego, right? And this is great because it's very versatile. So that you can play, you can vary, you can change individual parts without affecting other components of the entire workflow. But it's potentially very complicated for users and it involves a steeper learning curve, right? So how do we design software? And the approach in our team is actually to do both, essentially. But we do build the software following more of this playground approach, where we build the software around universal ingredients. Right? And we think very carefully about what these important ingredients should be. And then once you have a good foundation for implementing these, then we can package them into nice recipes, right? So I have this analogy really like cooking, where you want to focus on the quality of the ingredients, right? And you want to build the software around a really high quality of ingredients. And then users can prepare anything that they want, but you also give them at the end some specific recipes that they can use and just write out of the box. Which means that the emphasis is on the fundamental building blocks that give you flexibility, both to users and developers, right? Imagine there's a problem in one line of the code. Well, you can just change it because it's just one ingredient in the entire recipe. It's not the entire thing that you have to change. So now we're thinking about quantum chemistry, right? And this is literally a task that I was faced with in my work at Xanadu. How do we design new functionality in penny lane for quantum chemistry? And thinking about variational algorithms specifically, roughly speaking, what a quantum algorithm in quantum chemistry is trying to do is to prepare some representation of the state of a fermionic system using some states of a collection of qubits and somehow extract information, right? So you need both ingredients. You need to prepare the states and extract information. And one common approach to do this, perhaps the only approach that can be done on simulators and existing hardware, is to have specific circuit templates or circuit ansatz, of which there is an entire zoo, right? And here I'm giving you some of the examples of specific proposals in the literature. And it's difficult to navigate which ones are the best ones, what are the advantages and disadvantages of all the different approaches. And it's therefore difficult also to understand how to design software to actually allow users to run these algorithms. But if you took a look at the existence of algorithms for quantum chemistry and variational algorithms, it kind of seems to be suggesting this black box implementation, where we just code up a way to implement UCCSD and the qubit UCCSD and adapt PQE and so forth, right? And the user just goes and they plugs it in and they run their calculations. But this is not in line with the philosophy of how we like to build software at Xanadu and specifically for Penny Lane. So this raises the question, what are the universal building blocks of quantum circuits for quantum chemistry? What are these ingredients that we can use to build anything that we want, right? And once we have those, then we can package them into these nice, like standard circuits. So we want to design software so that we can build anything. And now this raises a research question, right? How do you build any quantum circuit for quantum chemistry? And just a quick reminder on how we usually represent quantum states for quantum chemistry. In second quantization under the John-Wigner mapping, essentially you have a collection of spin orbitals, and you think of particles, electrons occupying those spin orbitals. And the correspondence is that each qubit is assigned to each spin orbital, and then the states of the qubit, 0 or 1, denotes whether the corresponding spin orbital is occupied or not, right? And you can start from some reference states, and if you order the orbitals from low energy on the left to high energy on the right, this will be the two lowest occupied orbitals here in a system of 2 particles and 6 orbitals. And that can be your reference state. And then any valid state of that system, because you're not changing the number of particles, will have the same number of ones, the same Hamming weight, the same number of particles. And we can think of the differences between these states as differences that arise from the excitation of particles, right? So for example, on the right-hand side, here's a single excited state where I took one particle that had spin down on one of the lowest energy spin orbitals and then excited it to a higher energy one. And you can also think of double excitations. And in fact, any 2 valid states can be interpreted as different from some excitation. And then any general state will be some arbitrary linear combination, superposition of such states, right? So how can we carve circuits and build operations that map between these states? And this, so one important aspect here is the notion of conserving particles. So you want to respect that symmetry in the system, that you're only ever mapping between valid states that have a fixed number of particles. So what are the simplest particle conserving gates? And actually, one of the simplest one that can act at some trivial will act on a system of 2 qubits. And it may look something like this if you restrict it to having only real entries. Here I'm using an ordering where we have 0, 0, 0, 1, 1, 0, 1, 1, so that this gate is acting non-trivially only on the states 0, 1, and 1, 0, which can be interpreted as having the same number of particles, namely 1, right? And you're performing a rotation in that 2-dimensional subspace. This operation is first linking states through an excitation, and secondly, it is preserving the number of particles. It's an example of a Givens rotation. A Givens rotation is simply a 2-dimensional rotation in a subspace of a larger Hilbert space. And you can keep going further. You can think also of double excitation operations that are linking states that we interpret as differing by a double excitation, right? But perform a rotation only in a 2-dimensional subspace of these spanned by those states that differ by a single excitation, right? The chemists in the room may notice the similarities between things like the fermionic excitation operations, but we're not thinking of that. We're just thinking about the building blocks, right? What are the simplest building blocks for particle conserving unitaries, which are the basis of the gates that conserve this important symmetry of quantum states for quantum chemistry? And then we just thought about this very deeply, right? So can you actually build any circuit from these type of gates? If that's the case, then these will be great building blocks for our software, right? This given rotations. And that is in fact the main result of this paper. We have a lot of detailed proofs of how this works, a lot of examples, gradient formulas, you name it. Really, the intuition is very simple. If you look back at the action of this gate, it looks almost like a single qubit rotation, again, like a sigma y rotation. but now acting on a two-dimensional space of 0, 1, 1, 0. That's actually like a dual rail qubit, if you know what this is, perhaps on photonics. So this looks a lot like a single qubit gate. And indeed, our proof is essentially the same proof that two qubit rotations, and specifically controlled two qubit rotations, are universal, except that we're interpreting this subspace of 0, 1, 1, 0 as a dual rail qubit. But the important thing is that we proved that specifically controlled single excitation gates, which we denote also in the diagram on the right, because they can be acting in qubits that are not necessarily next to each other. It's universal for particle conserving unitaries, right? So this research paper that gives fundamental results on how we can build quantum circuits that preserve particle number was motivated ultimately by finding the right building blocks for quantum computing, for quantum chemistry, right? And one lesson that we learned is that maybe it's not exactly the single excitation gates that should be the building blocks, but Gibbons rotations, right? These are the way that we should be thinking, specifically from a software perspective, of building quantum circuits for quantum chemistry. And that's how we're building the entire library in PennyLane. It's around this idea of Gibbons rotations. Of course, users can do something else, but we're pushing this forward due to our understanding of the fundamental role that they play. And some immediate benefits that happen from doing this. We can think of new circuit ansatz. For example, there's a very simple variant of UCCSD trotterized to single level, which is simply saying, look, apply all the single or double excitation gates, but apply them as is Gibbons rotations, right? And so there's a new template that we can support. All these gates, we know how to compute analytical gradients. So automatically any circuit that you build, we know how to differentiate through it, right? Adaptive schemes, if you're familiar with them in quantum chemistry, well, now we can think of having adaptive schemes that have a pool of rotations, of gates that are actually given rotations. For simulation, it allows us to implement faster implementations than other types of gates, right? And of course, ultimately, all these templates from the zoo, we can still implement them, but now we can do it from the lens of these fundamental building blocks that we have understood, right? So again, by thinking about how to build good software, we ended up proving a specific result. That's fundamental research result leads to a research paper. So that's the first story. And I know I'm kind of running out of time, so I'll be very quick. Here's a different quick story. Now, we were thinking about what makes software easy to use. Let's ask a different question. What makes my software stand out? There are many people creating libraries, right? How are we going to build something inside of PennyLane that is going to be a distinctive feature, right? That potentially maybe no other library has done before. And you want performance, of course, you want a great user interface, you want great documentation, great community. But we were thinking also like maybe we can distinguish ourselves by having unique functionality. So it's some aspect of the things that you can do with the software that you can't do anywhere else. And that's a broad question, but one specific way that we try to tackle this is by understanding how to develop and implementing new quantum algorithms, right? And so maybe if you're familiar with variational algorithms for quantum chemistry, they usually look the following way. You have some Hamiltonian describing a molecule, and you have some circuit preparing some state that's parameterized, and you're trying to optimize those parameters of the circuit. Perhaps do some cost function that looks something like this energy function that I have here, some expectation value of the Hamiltonian. However, the Hamiltonian itself, which is often viewed as being a static object describing the system, is actually something that can be parameterized as well. For example, in terms of the coordinates of the atoms or the nuclei of the atoms that constitutes the molecule, right? And there's a lot of information that we can gain from the properties of the molecules by taking a look at derivatives of this energy function, right? Which incorporates this explicit dependence on the nuclear coordinate. For example, you can imagine what force do my atoms feel a specific configuration of the geometry of that molecule, so the positions of the nuclei, and that's simply the derivative of this energy function, right? So, and then something that you can do is to think like, well, maybe we can think of like something that we can do uniquely in PennyLane is to start thinking about algorithms for problems beyond just ground state and excited state calculations. Let's go further into new properties. And what does that look like? And so it's actually the same as the usual paradigm, except that now we're thinking more seriously about the Hamiltonian being parameterized, right? And then the algorithm is thought of not just minimizing over the circuit parameters, but minimizing also over the nuclear coordinates. So now we have a problem of joint optimization where we simultaneously optimize both the circuit parameters and the geometry of the molecule. And therefore, we end up with an algorithm for molecular geometry optimization, which is an important problem in chemistry. In fact, it's usually the input to electronic structural calculations. And as you scale into more complicated systems, it's not always clear what the optimized geometry is. Typically, people have some approximation of the optimized geometry, especially for molecules that maybe haven't been studied experimentally as much. So, through thinking about new functionality, we came up with a new algorithm for this specific problem, right? And how does this work? Well, the idea is you still need to be able to compute gradients with respect now, not just to the state and to the state parameters, but to the Hamiltonian itself, right? And we know how to do this. So for the first order derivative, simply the gradient of viscous function with respect to the nuclear coordinates is the expectation value of the derivative of the Hamiltonian itself, right? So then to support this type of functionality, what we want to do is to derive new methods to compute derivatives of Hamiltonians, right? Now, this can always be done, and this is something already that is natively supported in PennyLane using finite differences. And this is okay for small systems, but quickly you run into the usual problems with finite differences as well. So what we've been doing instead, and this is actually a collaboration with the Matter Lab at U of T, specifically with Teresa Tamayo Mendoza, who's no longer there, but also with Rodrigo Vargas, where we're working on a differentiable implementation of the Hartree-Fock method. It's a bit technical on the quantum chemistry side, if you're not too familiar with it. But what this allows us to do is to use methods of automatic differentiation. And this is actually following a lot of pioneering results from the Matter Lab, and specifically from Teresa and the publication that I have here below. And there's a package called Difficult. 1 minute. Okay, I'm almost done. Where what we do is that this differentiable Hartree-Fock solver allows us to compute exact Hamiltonian derivatives. And you can compute these derivatives not only with respect to parameters like the nuclear coordinates, but also with respect to basis set parameters, for example, contraction coefficients and exponentials, which allow us to optimize also the basis set for a specific molecule. Typically in quantum chemistry, you have good basis sets that are meant to be generally very good and are optimized for atoms, but not for molecules. So we can further optimize them. And this gives rise to fully differentiable workflows in quantum chemistry, where when you're running a variational algorithm for quantum chemistry, you're implementing and you're optimizing everything, right? The state and all the possible parameters of the Hamiltonian. And so we've worked hard to build this as a unique functionality inside of PennyLane. And through doing that, we came up with a new algorithm for geometry optimization, which leads to a research result. So I'm almost done. Just very quickly to wrap up before I take any questions. A reminder, we're still hiring at Xanadu. Any of you that are interested, you can find a lot of open positions here. And specifically for graduate students, we also have the residency program. This is an internship program, which is really fantastic. And the team puts a lot of effort into making it a great experience. So if you're interested, I do encourage you to apply. And I think that means I'm out of time. Thank you so much for your attention.
Thank you very much, Juan Miguel. Very interesting and different talk, especially explaining all these things that happen before the publication and the ideas are developed. That's really nice.
Thank you.
If anyone has questions, please ask in the chat and I will read the questions. Okay, Elishka, for instance, she had a question. I'm very excited to see such an active use of the DP stuff. What's your perspective on usage of these tools going forward, especially compared to variational methods and normal machine learning?
Sorry, so an active use of what? I didn't catch that.
The DP stuff, I don't know what do you mean exactly. Elishka, you can unmute yourself. And differential programming, sorry, yeah.
Oh, okay, and so then the question was like, what is a perspective on these tools?
Yeah, of the usage of these tools in compared with variational algorithms and standard machine learning techniques.
Yeah, so okay, maybe if I go back all the way to the beginning, this is, I was talking about distinguishing features of specifically for quantum chemistry, but PennyLane itself as a library, it's, if you had to summarize what is the core of PennyLane, is to build everything around differentiable programming. So the team has a motto, which is actually painful to keep in practice, which is simply that everything should be differentiable, right? So absolutely everything that you do inside of PennyLane should be differentiable. So the way that I think of variational algorithms is that it's they're one example of bringing this idea that you should be able to differentiate through every computation that you make into the quantum world as well, right? So it's just saying, and this was new, to be honest, right? A lot of work on quantum algorithms was based on like, well, I know what I'm doing. Here are the steps, 1, 2, 3, 4, 5, and I get the result of the outputs, right? And that's very powerful, but we've learned from what people have been doing in deep learning and beyond, that you can think a bit more broadly about computation, where if you can compute something, you can also differentiate through that circuit. And the ability to do so is actually very powerful. So I guess the shortest way to answer your question is that it's simply that the fundamental idea that our ability to differentiate through circuits is powerful, is something that everyone working on computation should embrace and understand, and then figure out how to exploit it exactly, right? So I don't think that we're doing anything that's like trying to go away from variational algorithms or anything like this. It's just trying to understand what do fully differentiable workflows look like in quantum computing, and specifically for my team in quantum chemistry, right? So for example, how can we design software and algorithms, right, that allow us to differentiate through absolutely everything that can be differentiated that appears in a quantum algorithm for quantum chemistry. So it's a core idea that I do encourage everyone to pursue and to understand, differentiable programming.
I have a question myself, which is talking about these main gate blocks, let's say, that you use to program all the algorithms. They are motivated by the theory behind everything, behind all of this. But what about the main blocks about the native gates that are accessible experimentally? For instance, you are also developing all these photonic chips. Yes. Are the gates that, like the one that you show, also native gates in these chips, or you need to develop other kinds of main blocks for them?
Yeah, it's a great question, and you could imagine something like hardware-driven research as well, or hardware-driven software, in the sense that indeed I didn't make a claim. So we are convinced, and it's part of the arguments that we make in our paper, that everyone working on the theory of quantum circuits and quantum algorithms for quantum chemistry should really embrace the notion of Gibbons rotation specifically as the fundamental building blocks, right? And I think that's something that has happened informally, but it's good to formalize it. Now, does this mean that when you're running algorithms on hardware, you should be exactly using these gates? Well, that's a slightly different question, because you have different figures of merit in hardware, right? In my simulator, I don't really care about certain things like decompositions. If it's a two qubit gate, I can apply any of them with equal ease, right? Or with equal difficulty. Not so true in hardware. So we know how to decompose these gates. It's part of like the great thing. So if you build any, maybe I should have added it here, right? Because you know how to decompose the individual components, you can decompose any algorithm that you build from them. But they're maybe not the most compact in the world, especially the double excitations, which are very important. They lead to perhaps not the shortest depth circuits in the world. So there is a good question of how to optimize that further. And it's one that I don't know the answer to. And frankly, I'm not sure the community knows the answer to that exactly, right? What are the best building blocks for quantum circuits that are now optimizing over circuit depth, for example, while still having some promise that they can attain sufficiently good approximations of the states we want to prepare? It's an excellent question. I'm not sure what the answer is.
Okay, thank you. Anyway, I mean, the discussion, it's great anyway. I mean, in the end, we have to find these main blocks, both for programming to develop new algorithms and also to find the implementations. But as you said, this could be two different questions. I think that we are running out of time, so we should move to the next talk. But thanks again, Juan Miguel, for this nice and original talk. And yeah, let's move to Eliška now.
Okay, thank you so much.